Okay, so we're going to diagonalize this one. And we're going to get a to the fourth and p d to the n power p inverse 4. We're doing a to the fourth, which yes, your calculator can do easily. So to get the eigenvalues, remember we do this. Okay. There we've worked that out. That will factor into +7 -3. Giving me lambda 1 equals -7. Lambda 2 equals 3. Now I shall look for corresponding eigenvectors. I didn't write that 7 very well. Two minus lambda. Then they're always times AB equals 0, 0. So that's 9. This is 1. We get 9A plus 3B equals 0. What do you need, Rowan? I don't have any. Nope. And 3A plus 1B equals 0.
This would be 1 and 9.
Yeah, 3 for B, 1 for A. One of them's got to be negative.
The other one.
And we'll do the other one. I'm doing it over here. 2 minus 3, 3, 3, -6 minus 3. That's -9. This is -1.
But where the heck are you out now?
And showing this work is a good thing for the IB exam. This case, A is 3, B is 1. So P,
This P it's the vectors, right?
Mhm.
The first like lambda 1 that is that your first column and then the second column is?
Yeah, and it doesn't matter if you switch the order as long as you switch all the orders.
Okay, so then in your D matrix, so to correspond, like if you put the lambda 2 on first, then you have the lambda 2 in
And
like
the top, yep.
and
And it's like the book used 3 as lambda 1 and -7 as lambda 2. So 1 over 1 minus -9. Oh, swapping doesn't do much. Negating just flips the signs. So 1 minus -9 is 10.
Okay, 2 pieces. With all one same groups. What the stupid thing? Yeah, one specific thing, don't go.
So that's my P inverse matrix.
Okay.
D has to be this way.
the whole like AC equals PD, that's just like a fact that I just accept.
That is the definition.
Okay.
It's how it is defined. Yeah.
Because I understand like the proof
Mhm.
after that, so like.
But why do you start there? Yes, that's how this is defined.
So I can remember PDP. Sometimes it's hard to remember stuff if I don't know why, you know.
So the idea with the eigenvalue is that they made that definition, and then the PD part is just doing both eigenvectors and eigenvalues in a single matrix. So let's finish this and then I'll explain that a little further. So first thing I'm going to do is show you the d to the fourth part, because I don't feel like writing it. So d to the fourth just ends up being this. -7 to the fourth, 3 to the fourth. The zeros don't. 0 to the fourth doesn't matter. 3 to the fourth is 81. 7 to the fourth is in the thousands. So this in PDP inverse form, which is what it wants, is going to look like this.
No, so it doesn't even want me to multiply them around.
No, it just wants it in PDP inverse form. Yes.
If I had to multiply them all out on a test.
You could use a calculator. Yeah.
Okay. Well, that's like just scientific calculator, essentially. I mean, if you have the matrix function.
Yeah. You definitely have you get a calculator for the entire DP exam.
Except for not the eigenvectors.
You have some features turned off, but you get a calculator. Does that feel a little easier now, second day?
Like it made sense yesterday, other than just like the why, but also like I understand what like
So
sometimes you don't always get to know that because you don't know the math yet.
there is some of that, but we started with this way back in 15.1.
Hang on. Wait, the inverse of P is it actually just, no, it's not. What am I doing?
So this was my original definition.
The
AX equals lambda x. This should
the
eigenvector
vector equals the eigen
value
value
times the eigenvector. And that's just how it is defined. Who came up with this and why, I don't know. But that is the definition of this. And so there are two eigenvalues and eigenvectors for a 2 by 2. When I put my two eigenvectors into a matrix, I get A times the P matrix. When I put my eigenvalues into a matrix, I get, well, a diagonalized times P. But here's the thing. Because it's a diagonal matrix, it's like an identity matrix, I can make that PD. It's not generally commutative, but a diagonalized matrix is, which is one of the reasons you want to get these.
P is the vector, the eigenvector.
Yeah. Well, I suppose I think it is commutative. This is commutative, where I can switch the order on a vector times a scalar. So that definitely is. So this can justify PD, and then
The eigenvalue is just a scalar.
yes. And then you multiply each side by P inverse. You get A
Makes sense now.
equals PD
This half of it does.
P inverse. And so that's the definition.
It's the APPD that's what's not.
It's just taking that definition and putting it into matrices. But
the eigenvalue is D because you start putting those.
yes,
Yeah.
you're putting it on a diagonal in there. Yes.
Like,
Okay, we're gonna go to the screen and look at the book for these last ones. These are a few applications of this. So a town has two schools, school A and B. Start the year, 10% of the students move from school A to school B and 5% move from school B to school A. School A has 280 students, school B has 320. So
school one.
We get this thing that we call a transition matrix. So school one this is school A. Start of the year, 10% of students move from school A to school B. This is what I need. So this is like A, B, A, B. So this is current state. This is new state. So school A keeps 90% of its students and gains 5% of school B's. So current is on top. This is essentially what Dylan's going to be doing with his IA. Yes. Mm-hmm.
And then school B
Is
loses, no, gains 10%
mhm.
and
Keeps 95% of theirs. Hmm. This is new state. And that does have to be that way. That makes sense?
Yeah, so it's like all in terms of school A, kind of.
Well, this is B.
Yeah.
B, 5% of its current go to A, 95% go to B. So what you can do is S1. Now you could just, do 90. You could do this by hand for the first one pretty easy, right? But if we want to do, 7 years down the road, these matrices become really nice.
Okay, so this is happening every year.
Mm-hmm. So we start with this. Let S1 represent the number of students in each school at the start of the next school year, where A is the number of students in school A and B is in school B. So easiest way to do that is take the transition matrix, which is a 2 by 2. I have to do T times my school matrix because it's 2 by 2 times 2 by 1. So if I want S1, the easiest way to do it is actually start by setting up this T that's in here in B and just do and multiply by my starting state. And you get this 268, 332. If you want year 2, you just take your T matrix, you square it, multiply by that.
I I thought that the 268 and 332 was the first year. So where did we get 280 and 20? Oh, it tells us.
It tells us.
Problem, okay.
So this is the enrollment. This is what it is after they do the switching, either the next year or, students all switch schools in the first 3 weeks. So if I want to do S2, let's go to the calculator and let's just plug these in. And I'm just going to store my matrices. It's not liking my second that. That's T, and we'll call my other matrix S. So now if I want to do T, and just take T to the second times S. And it looks like I will have 258 and 342. We do have to round these to whole students. Do not say I have 257.8 students. Part online. He's part online at the other school.
What's scheduled? Okay, that was awesome.
Write an equation Sn in terms of matrix multiplication of a diagonalized matrix for T.
This is PDP.
Yes, this is PDP. So let's let the calculator do these. So of a diagonalized matrix of T, because that's the one we're taking to a power.
We are going
To diagonalize, because S isn't taken to any powers.
so like we will be multiplying S by PDP and PDP
Yes.
all comes from
PDP inverse, yeah.
Vectors and values all come from T.
Yes.
Make those three matrices and then we times them by S. That's fine.
Yes.
Okay.
So
Does it matter where, like, what's, I mean, yes, it does. What side we multiply? S will be multiplied after.
S will be multiplied after.
And then S.
So let's go ahead and find them. Matrix and vector, advanced. Let's find our eigenvalues.
Once you like actually read the categories on the calculator, it makes sense first.
Hmm.
I was very confused.
At first.
And then it makes more sense. Like,
Okay, so that's my eigenvalues.
okay.
Advanced doesn't entirely make sense, but it does at the same time.
Gonna give you the eigenvectors in the same. It looks like it's a.
It's the same order. -1 and 1, -1 and -2.
So basically 1 and 2.
Yeah, let's do it as 1 and 2.
So -1 and 1 corresponds with 0.85 and 1.
That one should be negative. Let's do 1 and 2. The book does do -1 and -2.
Kind of like not necessary.
It's not necessary, I agree. D is this. And so d to the n becomes I'm going to take my P inverse, and I'm just going to use the negative so it matches up with what the book is. But yes, I feel like it's not necessary. So I'm going to enter that as a matrix, P, and then I'll do P inverse.
Because technically you could have like, if you multiplied one of the eigenvectors by a scalar,
Yes.
and then you put them in the P matrix, like would it mess up your P inverse if you had? Oh, but no, because if you keep it consistent with the.
If you keep it consistent,
But
it doesn't. If you changed that to positive, you'd have a different P inverse, but it would be consistent with its P.
Multiplying P by P inverse.
Hmm.
Okay.
So I'm going to store this as P just so I've got it. And then now we'll do P. The -1 gives me P inverse. And that is correct. So my diagonalized matrix that's to the end, but it doesn't really matter because it's 1. My diagonal, okay, I gotta write this down. So, okay, this is what it looks like. -1, -1, 1, 2, -2. D 0.85 to the n, 0, 0, 1 to the n. -2/3, 1/3, -1/3, -1/3 times 283/20. So what's actually happening as I go to infinity? 0.85 to the n So d to the infinity becomes 0.85 to the infinity, goes to 0. Just 1. So ultimately, I'm multiplying these matrices. P 0, 0, 0, 1. P inverse.
0, 0, 0.
It's P times.
Oh,
So I'm doing the d to the infinity.
and P inverse cancel.
No,
because
because
then
there's the d in between them.
Think about it.
So I'm now going to put this into the calculator, and I guess I'll just erase a little bit so I can see the calculator.
In the calculator, you are gonna put 0, 0, 0.
Yeah, I'm just going to put it in as a matrix and not bother storing that.
And it's like d to the infinity. No, like where it
Yeah. P times matrix 0, 0, 0, 1 times E inverse. And I already entered S. So eventually the school should stabilize at 200 kids in school A and 400 in school B.
Okay, that makes sense. Is it? If they're like losing the percent every year, it's
So
like
it will
the percent
continue.
how many is left from the year before, right?
Mhm. So 10% of school A leaving would be 20. 20 go to school B. They get
Yeah.
5% of school B is 20. So you get 20 going each way. And that's how you get the stable rate. So eventually you get to a point where the rate of change is the same for both. So two companies provide internet service for a particular area. ZipNet company gains 12% of the company customers from its rival Fast URL every year and loses 4% to Fast URL. So write down the transition matrix. This is the hardest part of this. Transition matrix. This is current on top. ZipperNet, Z, and let's do it over here. If ZipperNet loses 4%, it keeps 96, right?
Why? So stupid. I think when I was a kid. No, so this. With this. I'm just doing.
Does that make sense?
But we're making a transition.
Mm-hmm. So ZipperNet keeps 96% and loses 4%. Why did I call it T? F, fast URL.
I guess like I'm like it makes sense when you do it. So I don't think I'm gonna end
So
up setting up these matrices.
That's the hard part. That's the trick.
Yeah.
That's the part, the learning piece.
Tell me.
So that you have to get this current versus new. It has to be in that order. So I think about Z in its current state. It loses 4%, so that's 4% goes to F. That means it keeps 98%. The columns are current, the rows are new. So fast URL, ZipperNet gains 12%. That means fast URL is losing 12% to ZipperNet, meaning it has 88% left to retain.
So ZipperNet is current. Uh, since they're losing 4% every year, they currently have 96%.
That they retain
That they
Z to
retain.
Z,
They are gaining 12%
F
every
to
year.
Z. So that's yes, 12% of F's customers.
What F and Z where did that come from?
ZipperNet, Fast URL. I just am shortening up their names.
If fast URL, so like they're losing these customers to the other one.
Mhm.
Okay.
Nobody's losing customers to not having internet.
Or are rows named Z and F? Shouldn't it be like gained and lost or like?
So I'm naming them Z as ZipperNet. ZipperNet's current to ZipperNet's new. Fast URL's current go into ZipperNet for the next year. ZipperNet's current going to Fast URL the next year. Fast URL to Fast URL.
Okay.
This making some sense? This is the hardest part. That's the challenge and what,
They keep and what they lose to the other.
yes,
That's how the.
yes, yeah,
things work.
yeah.
That makes more sense.
So write it down in PDP inverse form. You can do that.
Yeah.
I'm just going to tell you what it is. Not that they gave P inverse in the answer key. So P, you get eigenvalues of 1 and an eigenvector that corresponds with it of 3, 1. You get eigenvalue 2 of 0.84, and you get -1, 1. So 3, 1, -1, 1, 1, 0, 0.84. I guess I need to get P inverse. I'm just going to do it on my calculator. And then the P inverse here is 1/4, 1/4, -1/4, 3/4. So it asked me to write an expression for how many they'll have after X years. Or N years.
We're just gonna do like D to the end.
D to the N, yep.
So 1 to the N, 0, 0.4 to the N.
Mm-hmm.
And like it's the same concept because if we go to infinity, it'll be 1, 0, 0, 0.
Mm-hmm.
Almost. Ooh.
And 45,000. So let's go to our calculator. We'll do this. The N will be 1, yeah, 0, 0, 0. Okay, I can see the matrices on my calculator, so I'm going to clear all of these. And I'm not going to bother saving because I don't think I need to do this again. 3, -1, 1. And yes, the diagonalized matrix, the 0.84 to the infinity goes to infinity. And my P inverse matrix. And I just made those decimals because I could. And then it was 45,000 and 52,000. And it was important that I put them where I did. Oh, when I set it up, I should not have put the zeros. I don't know why I put the zeros.
Where do we not need this?
I had 45,000, 52,000, which I think might have still worked. Let's see if that would work. I'm going to copy and paste and delete my final matrix, and let's put it in as a diagonalized version.
Cause that's S, or well, I don't know if it's S and, yeah, is it S in this?
S is really the first one, but I think no, that does not work. If you add those together, it would work. Yeah, if you add by row, yeah. So not the second one.
Like if you were to matrix multiply and that was
Yep.
your last one, you'd be adding.
Yep.
Sorry, hey guys, that's process, so that means you can't.
So yes, don't do the zeros.
You.
Does that kind of make sense? The
This was the internet one, so the last one was just the.
stable state
They
is
started with.
For right now.
yeah, the last one was what they started with. The stable state is 72,750, 24,250. Yep. And that's a transition matrix. We will be using them again in unit 3 and then in unit 4. And
Okay.
kind of in the middle of unit 3, we'll use them for, you can use them for geometric transformations. Those are not as, those are a little easier, but they do this transition matrix thing with Markov chains at the end of statistics, which is what Dylan is trying to use for his IA. Okay, that's it. Yep.